بسم الله الرحمن الرحيم ربي اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي سلام عليكم ورحمة الله وبركاته. Last time we spoke about the earth and the moon, but today we zoom out much further to the biggest object in our sky, which is the sun, the star without which we quite literally would not be existing today. But before I begin today's talk, I would like to take a moment and thank each and every one of you for all your kind words and the feedback that you shared after my previous lecture. It means the world to me, and it encourages me to keep learning and preparing these sessions with more care, because I don't see myself as a teacher, rather I see myself as a fellow learner who is sharing just what I find fascinating in the creation of Allah subhanahu wa ta'ala. So please, by all means, continue to share your thoughts, suggestions, even corrections if there are any, because as I see it, we're all discovering this together. With that said, let's begin our journey into the solar system, or the heart of the solar system, the blazing engine that powers our world. Can I get the next slide, please? Looks like my remote's not working very well. And again. Right. So when you look at the sun through a telescope, don't. It's not the best idea. You'd go blind almost immediately. But if you were to use a proper solar filter, what you'd actually be looking at is just the outer skin of the sun, the one that's visible to us, called the photosphere. And as shocking as this may sound, our sun isn't just a huge ball of fire. It is, yes, but it's a lot more than that. It's got layers, just like our Earth. Looks like I have some technical issues. But it's also got layers just like an onion. I had to add the onion part because that's what most comparisons of layers use. On the inside, the temperatures in the sun rise to over 15 million degrees Celsius. I'll be saying this number a lot. A small reminder, Jahannam is a lot hotter, if I'm not mistaken. So again, just a little anecdote that we ask Allah subhanahu wa ta'ala to save us from this. So at the core is where hydrogen atoms are squeezed together under immense pressure to form helium. And this is a process called nuclear fusion. Most of us have learned this in school, but I will expand further on this in my other lecture about stars. So, as you can see, if I can use the pointer here, you have the photosphere there, right? And that is actually the third layer of the sun. There's two more after it, but obviously we can't really see it. The chromosphere and the corona. All of this is not important. I will not be giving a test later on. So now, although the core of the sun sports a blazing 15 million degrees. I told you I'd be saying this number a lot. The outer layers are actually significantly cooler than it is on the inside. So cool, in fact, that we have those temperatures here on Earth. You heard that right. We have temperatures similar to the photosphere of the sun and even hotter than it right here on Earth. For reference, the photosphere's temperature is around 5,500 degrees. So imagine, from the core, you have 15 million, and then just outside the sun, you're at 5,500. Huge drop. And that is the temperature that travels to us. Obviously, we don't get 5,500, otherwise we'd be quite cooked. Next slide, please. So you might be asking, where on Earth do we have these temperatures? Next. So we have them, one, in industrial welding arcs. That little ball of fire, depending on the type, they can range from 6,000 to 20,000 degrees Celsius. Next. But then we also have lightning bolts. These can reach upwards of 30,000 degrees Celsius. And it's incredible to think that phenomena right here on Earth can rival, albeit in brief moments, the blazing surface of our star. But actually, let's take a quick tangent about lightning, because it's too fascinating to skip. Next, please. Next again. So lightning starts in big storm clouds. So I'm going to try to make this as easy as possible to understand, because most of this is what I learned back in school. But warm, wet air rises up into the sky, obviously. And as it cools, because the higher you go, the colder it gets, it turns into tiny water droplets. And then some of these droplets freeze into ice crystals. Now, inside the cloud, these droplets and ice pieces are bumping into each other, like, you know, a giant bumper car game. And every time they collide, they swap bits of electric charge, so, you know, positive and negative. What happens then is the lighter, so the positive bits are more lighter. So they float to the top of the cloud, while the heavier and negative bits, like hail, they sink to the bottom. So now, if you look at the cloud, it starts to resemble something we already use in our day-to-day lives, and that is a battery, right? We have positive at the top, negative at the bottom, or if you flip it, you have either. Now, what ends up happening is that big negative charge at the bottom of the cloud there, it actually pulls on the ground beneath it, because there are positive charges on our ground. There are both positive and negative, but mostly positive, because unlike forces attract. So it drags up the positive charges from the Earth's surface, as you can see there. And so it's like the ground and the Earth, the ground and the Earth. The clouds and the ground are staring each other down until like this, you know, huge fight is going to happen, because they're building up tension. Because when this happens, we're basically creating an electric field. So basically, in this area here, there's an electric field that's been formed. And then what ends up happening is when the difference in the charge gets too strong, so when there's a lot of negative or a lot of positive, the air between them can't block this anymore. Now, in physics, this is called the insulating capacity of the air. So once that gets overpowered, the air quite literally breaks, and you have this giant spark that jumps through the sky, and that spark is what we see as lightning. So again, this is electric charges just made because water went into the sky, and now you have lightning flashes. And now here's where it gets really intense, literally, because this spark itself heats the air around it to an insane 30,000 to 33,000 degrees Celsius. That's 5 to 6 times hotter than the surface of our sun. Just a quick reminder of the states of matter before I continue, in case anyone's forgotten. In solids, the particles are tightly packed, and they barely move. They only vibrate in place. So think like of a block of ice, right? It keeps its shape because the particles are locked together, right? In liquids, particles are still close, but they slide past each other freely, and that's how water can flow, fill containers, and even change its shape, because particles can move around. In gases, particles are far apart, and they just zip around at high speed, bouncing off each other and basically filling any space they're in. And air is mostly gas. So these are the classic states of matter. There's around 5 more, but they delve very deep into physics and don't really fit for this explanation. Anyways, when lightning strikes, the air around it heats up so incredibly fast. Imagine 30,000, 33,000 degrees like that in a split second. And the particles in that air suddenly start moving and expanding wildly. So imagine like a tightly packed group of people standing still, and then all of a sudden everyone's just run off in different directions, right? That rapid expansion pushes it pushes everything out. It pushes all the air particles out in every direction, and that creates a shock wave. And that shock wave is what we hear as thunder. So that's why you always see lightning before you hear thunder, because obviously the flash and the boom start together, but light travels faster than sound, and so lightning wins the race. Sometimes you may not see lightning, you may not see a lightning bolt strike the ground, but lightning is literally the only reason thunder exists. It's because the air is heated up to that speed, and that's why you have these booms. So there, basically, I tried to make it as visual as I could. Now, just that, okay, so now that tangent over, let's move back to this big flaming ball of gas that's at the center of our solar system. So just like lightning briefly reaches temperatures hotter than the sun's surface, the sun itself sustains extreme heat continuously. Because remember, lightning is a second. It's light. It's like somebody flashed something and it's off. But the sun keeps this temperature always for as long as it's been alive. So just its core, remember, again, 15 million degrees Celsius, probably more. And that heat is hot enough to fuse hydrogen into helium that produces the light and energy that nourishes every corner of our planet. Up here, you'll see deuterium and tritium. These are still hydrogen. These are isotopes of hydrogen. They just have an extra proton, if I'm not mistaken. The energy, they get fused because of the heat and the pressure, and then that releases the energy, which then comes to us. So the light that we see from the sun doesn't reach us immediately. And this is one of the coolest things that I personally believe. So photons, the tiny packets of energy, basically light. Light is photons, right? These particles of energy. They're created in the sun's core, but they have a long journey to escape. They bounce around the sun for thousands, even hundreds of thousands of years, slowly making their way to the photosphere, that layer that we talked about, before finally shooting across space into Earth. If you counted how long photons took to make it through each layer of the sun from the core before finally reaching us, that's around 10,000 to 170,000 years. So the sunlight that you get today on your skin when you walk outside might have been born when humans were still using stone tools, like before any of our grandparents were born. That's when the sunlight that you see today was born in the sun. It took it that long, because every time it tries to move from the core, it bounces into electrons, it bounces into hydrogen nucleuses, so protons. Until the point that it gets to escape the sun, it takes 100 to 170,000 years. Right. So whether it's lightning on our planet or the sun itself, the same principles of heat, particle motion, energy transfer, all of these apply, just on vastly different scales. This lightning is very small, 30,000 degrees. The sun, 15 million degrees. Now, these extremes help us appreciate the precision, the balance, and the power of our universe. Now that we've looked at what the sun does, or has been doing right now, shining, radiating heat, fueling life, let's zoom out time-wise and ask a bigger question. Where did the sun come from? And where is it going? Is it even going anywhere? Because here's the surprising truth. Shock. The sun hasn't always been there. And it won't always be here either. It has a story, a beginning, a middle, and eventually an end. So the birth of the sun started approximately 4.56 billion years ago. This is beginning of our solar system. The sun was born when it was nothing more than part of a giant cold cloud of gas and dust drifting quietly in the Milky Way. There was nothing that was going on. It was quite literally like that, just a gas and dust and cloudy looking thing. Huge. Again, I must stress the weight. This is heavy. That's how gravity comes into play. Now, most of this was just hydrogen, waiting silently. But then something dramatic happens. Scientists think, right? Scientists think that nearby, a star exploded into a supernova, sending out powerful shockwaves across space, and this disturbance shook up this calm cloud, and as parts of it began to collapse under their own weight, because now gravity was set in motion, gravity started pulling everything inward, tighter and just closer. And now, as this cloud collapsed, it began to spin. The same way like you would see, I'm not sure how many of you skate here, but when somebody who skates brings their arms closer in as they're spinning, they spin faster than when they put their arms out because of resistance. So basically, the pressure in the center as it spun grew unimaginably. Temperatures soared into the millions of the degrees that you hear today. And then it happened. The first nuclear fusion. The temperatures were so high that 2 hydrogen atoms could be fused together to make helium. And the moment this happened, it started releasing tremendous amounts of energy. And that was the moment the sun lit up for the first time. A star was born, and around it, leftover gas and dust started sticking together to form planets, including us. I even put this here. So basically, this is all gravity that goes into it. This is when the temperatures got too high to the point where it started having nuclear fusion. And then slowly, as you can see, the dust starts revolving, and you get the planet. And what would you guess? The Quran describes this very stage of creation in Surah Al-Fussilat, Surah number 41, ayah number 11. Allah subhanahu wa ta'ala says, Bismillahir Rahmanir Rahim, ثُمَّ اسْتَوَى إِلَى السَّمَاءِ وَهِيَ دُخَانٌ فَقَالَ لَهَا وَلِلْأَرْضِ ائْتِيَا طَوْعًا أَوْ كَرْهًا قَالَتَا آتَيْنَا طَائِعِينَ. Then he turned to the heaven when it was smoke. Does that remind you of anything? He turned to the heaven when it was smoke and said to it and to the earth, come into being, willingly or unwillingly. And they both replied, we come willingly. So this cosmic smoke of gas and dust that modern science describes, the Quran already mentioned it 1,400 plus years ago. And we know this already. Us as Muslims, obviously, a lot of things in science that are being proven day by day, we've already known this because we've already read it in our book. Allah subhanahu wa ta'ala has already explained this in such detail, because how else would you call this if not a cloud of smoke? Right? So the heavens and their earth, in their unformed state, were commanded to submit. And they did. And this is a reminder for everything, that everything in creation, from the greatest star to the smallest grain of sand, obeys the order of Allah subhanahu wa ta'ala. The sun today is in what we call scientifically the main sequence. It's basically adulthood for a star. It's stable, it's reliable, and it's hard at work fusing hydrogen into helium in its core non-stop. But every single second, the sun is fusing 600 million tons of hydrogen. 600 million tons every single second. Not minute, not hour, second. It's losing 40% of its weight every second. And it still has the ability to do this. It's been doing this consistently for billions of years, ever since it began. For the 4.6 billion years that the sun has been alive, it's been losing 600 million tons of hydrogen every second. Now, I don't know how to explain this, but that's a lot. That's a huge number. So in star terms, right now, the sun is middle-aged, not young, not old, just steady. And it has plenty of fuel for about another 5 billion years. So, we should be fine for now. Over here, I've tried to explain how the sun kind of keeps itself together, because the fusion in its core pushes out energy, right? And gravity, because the core is so dense, tries to pull everything in. So now it gets to this point where the fusion energy that's pushing out is the same as the gravity that's pushing everything in, and so it comes to a balance. And that's how it's become stable. That's why it is the way it is. It's, again, such a perfect balance, such a perfect size, and such a perfect distance away from us that it's shocking to think anyone would think that this happened by chance. But obviously, nothing lasts forever. Eventually, the sun will run low on hydrogen. I mean, it's losing 600 million tons a second. It's going to run out at some point. And when that happens, everything will change. The core will start to shrink under gravity because, as I just explained, it won't have the energy to push out because it doesn't have that fuel anymore. And so gravity is going to start winning this race. And it's going to, push the core down. Now, what this actually does is now the outer layers of the sun balloon outward. This happens to most stars, the sun's size. The sun will then swell into what we call a red giant. Now, a comparison between, I wish I actually put a picture, but a red giant and our sun, incomparable. Like compared to a red giant, our sun looks like that, right? And so imagine the sun not as a small, bright circle that we see now, but actually something so massive, it takes up half the sky. The sun swells into what we call a red giant, and it will grow so large that it could swallow Mercury, not could, it will swallow Mercury, it'll swallow Venus, and possibly Earth. Now, does this remind you of any signs of the final day? We are told the sun will come closer to the Earth, and the Earth will be scorching red. But I want you to picture this from somebody standing still. From my perspective, if something was on that side of the mosque, and it got bigger and bigger and kept getting bigger, to me, since I'm standing still, I would see it as coming closer, because the bigger it gets, the closer it gets to me. So, in Surah Al-Yasin, Surah number 36, ayah number 38, Allah subhanahu wa ta'ala says, Bismillahir Rahmanir Rahim, وَالشَّمْسُ تَجْرِي لِمُسْتَقَرٍ لَهَا ذَلِكَ تَقْدِيرُ الْعَزِيزِ الْعَلِيمِ. The sun travels for its fixed term. That is the design of the Almighty and All-Knowing. The sun travels for a fixed time. So we are literally told, even the sun will die. So for a while, the sun will burn hotter and brighter in this stage, but it'll also be very, very unstable because the gravity and the fusion energy do not match, right? So it will shed those outer layers into space because they just keep expanding, and then it'll get to a point where the sun can't handle this anymore. And so it'll then create a stunning cloud called a planetary nebula. If you've ever seen a ring, if you've never seen the Ring Nebula, this is what that looks like. So that is what our sun will one day become. This is not a glimpse into the future. This is an actual image of other stars that have gone through this, right? So obviously, that is the core, and then everything else just withers into space. And what remains at the very center? Just a very hot and dense core called a white dwarf. Now, so there's no more fusion, there's no more energy production, just a fading member of what once was a mighty star. And over trillions of years, this ember will slowly cool down and then, fade into darkness. So, again, the sun, as it is now, It gets bigger. It'll get so big to the point where it'll almost swallow Earth, and then it'll have a ring nebula. And then as all of this sheds and goes away, we just have, I'm blocked by my camera there, but just a little piece left. And then this, it doesn't do anything. It doesn't eat, it doesn't take in energy, it doesn't do anything. It just disappears. It's like we're waiting for a piece of coal to just stop burning. That's it. That's the end of our sun. Now, you might ask, why should I care about what happens billions of years from now? But here's the thing. The very reason we exist at all is because of this cycle. The sun is not the first star, and it won't be the last. The heavy elements in your body, the carbon, the iron in your blood, the calcium in your bones, all of it was forged in the life and death of an earlier star. Because all of these elements existed in stars before the Earth existed. And the Earth, as I mentioned, was basically a byproduct of the sun forming and rotating all these dust particles around it, and that's how we came about. So basically, everything you have in you was once in a star. Just think about that. So whenever we talk about the sun's birth and death, we're not just telling the story of a star, we're actually telling our story as well. I must admit, when I was younger, right, I often looked at the pollution on our Earth, and I thought, why not just throw it into the sun? Plastic, nuclear waste, everything, you know, problem solved in one fiery swoop. And I'm sure I wasn't the only one who thought that. I mean, who hasn't looked at, you know, like a massive, you know, mountain of rubbish, or, you know, seeing people bury nuclear waste underground, even polluting our oceans, and just thought, instead of doing all this, why don't we just shoot it into the sun? But, as it turns out, for everyone who thought that, I did some research, shooting something into the sun is a lot harder than, you know, just pointing a rocket at it and shooting. And here's why. So, when you launch a rocket off of the Earth, it doesn't just have to get off the ground. It needs to escape the gravity of the Earth, right? The thing that's keeping us here, which is why scientists talk about something known as escape velocity. Now, velocity is speed, and escape, the reason it's called escape is because it's the velocity needed to escape the Earth, right? To escape being pulled back. So, imagine like throwing a ball or throwing a remote. If I throw it, if I toss it gently, it falls back. If I were to use more energy, I don't want to because I might hit the ceiling, but if I use more energy, it would go. Now, you throw it harder and it goes, you know, further. But if you throw it hard enough, it would just keep going and never come back because it would have reached the speed to escape. Obviously, no human can do this. If you can, please get in touch with me. You might be the next breakthrough in space travel. For Earth, that magic speed is around 11.2 kilometers a second. That's very quick. I mean, it's per second, not per hour. 11 kilometers. I could run faster, I think. Or roughly 40,000 kilometers an hour. Right? So now, here's the tricky part. When you launch something into space, it already inherits the Earth's motion around the sun. Because if you remember from my previous lecture, we are still moving around the sun at 30 kilometers a second or 108,000 kilometers an hour, right? We are being swung around. So now when you launch something, you don't just, you know, launch here and the Earth keeps moving. You move with the momentum of the Earth, right? So we call this speed the orbital velocity. Just like escape velocity, this is orbital velocity. So this sideways movement of the Earth keeps our rocket in orbit of the sun instead of letting it fall, you know, straight in. So that's why this is the sun, by the way. It's not a good image, but so our rocket would just be going around the sun instead of going into. Now, the sideways motion that we have and the gravity from the sun is what lets us revolve around the sun. So basically, the best way I could give an example of this is if I tied a ball to a string, right, and I held it like this, the ball would just stay down. But if I started to twist or spin, the ball would now revolve around that center point. But the moment I let go, the ball just comes back down, right? So now imagine the sun being the hand and then doing this, and then the earth is what revolves. Now, if for some reason, right, the sun lost all of its mass at random, the sun just lost all of its heaviness, right? We would be shot into space at 30 kilometers a second, right? So it's like me holding this, and then my string breaks. The ball just goes in whatever direction it was facing, at whatever speed it was going, right? And if we somehow lost that speed, so if I just stopped the string immediately, the ball would fall straight down. So if we somehow lost our speed, so if you see here, the sun loses all the energy and we just get shot into space. And over here, the sun still has its mass, but we lost our speed. And so we would just get sucked into the sun. And that's it, over for us. So to actually crash something into the sun, we need to slow it down enough to cancel out the orbital velocity of the Earth, letting the sun's gravity pull it inside. Now, slowing down in space is not easy because there's no frictions, there's no brakes. You can't just stop because you'll always keep floating. There's nothing to stop you from moving, right? So you have to use fuel or fire rockets in just the right direction to shed speed. But then this means huge amounts of fuel. Ironically, the closer you get to the sun, the more fuel you need, because orbital speed increases as you get closer. In fact, it's actually more fuel efficient to first head outward into the outer solar system, slow down there, and then, you know, let the sun's gravity pull you in. Now, I'll explain this line here. The closer you go to the sun, the more fuel you need, because the orbital speed increases. So like Earth is traveling at 30 kilometers a second, right? But Mercury, the closest planet to the sun, is traveling at 48 kilometers a second. Because it's much closer to the sun, there's a lot more speed that it needs to be able to stay within that orbit. So that's basically option one, carrying enough fuel to brake in space. It's technically possible, yes, but practically quickly becomes a bit, you know, insane. Because to slow an object enough to drop it straight into the sun, we'd need orders of magnitude more fuel than any rocket we've ever built, just to deliver, you know, a few tons of rubbish. Basically, we'd have to go the opposite way of orbital velocity to carry it out. And I tried to show this in that image. So basically, if the orbital velocity moves the rocket that way, it needs to have a thrust exactly the opposite way so that they cancel out and basically slow the rocket down. Now, to put into perspective the fuel that you would need, the Saturn V, I don't have any images, I do apologize, but this rocket took humans to the moon. This is the largest rocket successfully flown, and it needed 2 million liters of fuel just to reach escape velocity, not to get to the moon, just to escape Earth's gravity. This, again, just to give you an idea of how big this rocket is, that's 110 meters tall, over 110 meters tall, so bigger than the Statue of Liberty, if you count the base as well. And it could lift about 140,000 kilograms. This is like launching 30 adult elephants into space at once, just, you know, because I don't know why you'd want to do that, though. Now, imagine multiplying this effort to send something into the sun. You would be talking 100 million liters of fuel or more. A scale so massive that even the Saturn V would look tiny in comparison. So clearly, option one, not good. It's possible, technically, but it's laughably difficult. Now, this brings us to option two, gravity assists. So instead of trying to slow down a spacecraft with fuel alone, we can cleverly use the natural motion of planets. So when a spacecraft approaches a planet in the right way, it can basically slow you down, and essentially the planet's orbital energy is transferred into the aircraft. Now, again, to explain, if a planet is moving this way, relative to the sun, let's imagine I'm the sun, and a planet is moving this way relative to me, if my rocket was floating and it was going this way, this planet would kind of pull on this and slow it down, and it would then be able to fall in. Again, just to give a better explanation, I tried to put an image as well. So this planet moves this way, but we push our rocket to go the other way. So basically, you know, the rocket's going by and the planet's like, hey, you know, slow down, just wait, and then obviously it slows it down. Now, are both of these methods possible? Technically, yes. But are they worth the risk and the money? Not in the least. Even the Saturn V, the most successful, largest rocket ever flown, or successfully flown, it had a 2 to 3% failure rate. Obviously, they didn't fail, but you can't risk something like that with something like nuclear waste, because, you know, one mistake and you have just radioactive rain, right? You put nuclear waste on a rocket, you try to launch it, it explodes. Now you've spilled everything. So while we can't throw nuclear waste or plastic into the sun, we can send extremely fast and well-protected instruments to study it. And this is where the Parker Solar Probe comes into play. It was launched in 2018, and it is now the fastest human-made object ever. And it accelerates to around 700 kilometers an hour as it swoops, 700,000, sorry, 700,000 kilometers an hour as it swoops close to the sun. And its mission, when it was launched in 2018, was to dive into the sun's outer atmosphere and to get unprecedented measurements. And this helps us understand the sun in ways that were impossible before. Now, what exactly it's told us so far and how it's gotten there is another topic in and of itself, and which I will expand on in my future lecture about stars, inshallah. But this, again, just to explain, it has touched the sun. It was launched in 2018. It has had around 12 orbits around the sun. It has touched the corona of the sun. So again, if you remember the layers, photosphere, chromosphere, and then the corona. The corona is the very outside. We don't see the corona. It's the one that you see like a halo when there's a solar eclipse. If you remember the pictures that I put in my last lecture, there's like a ring of light around the moon. That's the corona. And this guy has touched it. And again, the reason we were able to send this is because we found out that the sun's surface is actually not as hot. Because, I mean, lightning is 30,000 degrees, sun's surface, 5,500. So with good heat shields at the front there, this is a heat shield, it blocks that. What it does is it takes the magnetic readings, trying to understand why the sun does what it does, and then as it has this elliptical orbit. By elliptical, it means like an oval. So if this is the sun, and this is the solar probe, it goes close to the sun, and then it goes downwards, and then it goes back. So when it's away, when it's the furthest away from the sun, it points its antennas to the Earth, sends us all these images, all this data, and then goes back. And so far, if I'm not mistaken, it's sent around 2.1 terabytes of data so far. And I believe its final revolution around the sun will be later, because it's getting too close to the sun now. It's probably going to melt before it even does anything. And so, when we look at the sun, the beginning in smoke, the present as a steady source of life, and its future collapse, we're reminded of two things. First, creation itself is temporary. Even something as mighty, as blazing, as central as the sun has an expiry date. I speak to everyone and I speak to myself. If the sun itself will fade, What about me? What about my short time on this earth? Second, everything follows the precise decree of Allah subhanahu wa ta'ala. Stars don't burn forever, planets don't orbit forever, and even time itself is moving towards an appointed end. And yet, I'm going to say I, so I don't offend anyone, I often live life as though time won't end. So when we see the sun every morning, the same sun that's brought us the light today, instead of just thinking, oh, nice weather, feels warm, we can choose to see it as a reminder. Allah subhanahu wa ta'ala placed it exactly where it needs to be, burning exactly as it should to sustain life, neither too close, no too far. If it was slightly off in either direction, there would be no us. We'd either freeze or burn to death. Allah tells us, again, in Surah Al-Anbiya, Surah number 21, ayah number 16, Bismillahir Rahmanir Rahim, وَمَا خَلَقْنَا السَّمَاءَ وَالْأَرْضَ وَمَا بَيْنَهُمَا لَاعِبِينَ. We did not create the heavens and the earth and everything between them as a game. So this isn't random, it's intentional, it's purposeful. So yes, the sun will die one day, but until then, every ray of sunlight is both a mercy and a reminder. A mercy because it sustains us, but also a reminder that all power belongs only to Allah subhanahu wa ta'ala, the only one who lit it in the first place and the one who will one day extinguish it. And maybe that's the real takeaway today. Don't just study the sun as a star. Study it as an ayah, as a sign, pointing us back to the one who made it. We pray to Allah subhanahu wa ta'ala to give us the opportunity, this and many more opportunities to marvel at His creations and to make us one of the thankful ones and ones that notice His signs and praise Him for them, inshaAllah. That is the end. Wassalamu alaikum wa rahmatullahi wa barakatuh. Of course, I will welcome questions, but I feel like I've taken a lot of time today. Please, man. Yes. Okay, so the sun's corona and the corona we had on the earth are very, very different things. This one is a virus. The outer layer of the sun is just called the corona. Most stars also use this naming nomenclature. I did talk about lightning. Right, so the question is, will lightning come to Earth and will it burn us? I mean, there have been people who have been struck by lightning. Some have survived, some have not. But yeah, lightning happens every day. There's different types of lightning. There's lightning that happens between clouds. That's why when you look up, you'll just see like clouds go white and then just Earth. And then there's lightning that goes between clouds as well. So it's always there. Okay. Any more questions, or is everyone hungry today? Yeah? Okay, so. Assalamu alaikum wa rahmatullahi wa barakatuh. We have a loud salawat, please.
بسم الله الرحمن الرحيم السلام عليك يا رسول الله السلام عليك يا أمير المؤمنين السلام عليك يا فاطمة الزهراء سيدة النساء العالمين السلام عليك يا حسن المجتبى السلام عليك يا